Okay, so thank you to the organizer for giving me this second opportunity to speak today. The topic will be quite different from the previous one. So especially I will mostly talk about classical TT-bar-like perturbation in relation. So this is work done in collaboration with Riccardo and Jacopo. So I'll start again by some recapitulations and some brief recapitulation of TT-bar history. Okay, so well, essentially, really, all the motivation of studying TT-bar-like perturbation or anyway irrelevant perturbation came from the study of the thermodynamic ansatz, as very well explained by André this morning. So, coming from the integrable model community, we really used to start from try to find the S matrix, or then from the S matrix, the thermodynamic ansatz equation. These are really quantum equation, and essentially changing the volume of your system, you can flow between the ultraviolet small volume to the infrared large volume. So initially, I mean, this idea worked only for a massive scattering model, so that this implies that you have a non-trivial, a conformal field theory in the ultraviolet, but a trivial ultraviolet fixed point lead. At a certain point, Alyosha Zamolodchikov introduced the concept of scattering matrix for massless particle, and then it was possible then to describe also non-trivial flow between two conformal field theory. So you start from a conformal field theory describing your ultraviolet, you perturb it by a relevant integrable perturbation, and you might flow to a non-trivial infrared fixed point. And so the first stunning example was related to this famous tricritical Ising to the Ising fixed point conformal field theory along this critical line. Okay, so when when this was discovered, of course, so now we have some exact result that we can study the neighbor of the of the infrared conformal field theory and look at the perturbing operator leading attracting perturbing operator that would be irrelevant operator. So the initial hope was really very big, but then after a few numerical and some analytic results, I think we stop. Okay. So the main issue is really how, if you start from the infrared theory, how to build up a consistent theory which eventually is a conformal field theory in the ultraviolet. So this is a nice job that Changrim and Andrea are doing now, and it's I think they are great. You know, they are getting very nice results. Okay. So during the study, the first operator came out from this critical to criticalizing was the TT-bar operator. So the first time it was really introduced was by Zamolodchikov in that paper. But since we were studying, or he was studying close to the infrared fixed point, it was just T, the holomorphic type T-bar, holomorphic time the anti-holomorphic part of the TT-bar operator. Then later, using within the framework of form factor for correlation function, then they realize they need some calculation, and they some calculation, from some calculation came up that this TT-bar operator fulfills some nice factorization property. And so this motivated Sasha Zamolodchikov to write this 2004 paper, which is at the base of what we are doing now. Okay. And of course, there were many other people like Sardo, myself, Chandrin, that were working on this master flow and try to understand sterility factor, etc., etc. But essentially, we were stuck for a long time, and till this Dubowski et al. Paper came out, and when they used they use a thermodynamic Bethe-Ansels equation to get the spectrum of the Nambu-Goto theory in the static gauge. And then for us, it was very simple to understand that was the TT bar operator behind. And so this everything started. And since 2016, we know that I think the whole community made amazing progress in that direction. Okay, so the definition of the TT bar operator is skipping the name when so it was traceless, so close to the a conformal fixed point, but is actually the determinant of the stress energy tensor. So if this tells you immediately that it's really a universal perturbation, and indeed we think or we believe that we can get the result and this Burger equation, which is independent of integrability. So you can always, even if your theory is non-integrable, you can always get some add to it the TT bar operator. Okay, so for my current purposes, I'm not interested in the, so I would be, yeah, in general, I'm always very interested in the quantum version, but we cannot do much if we move out of the 2-dimension, and in upper dimension, we don't know really how to treat at quantum level TT bar-like perturbation. Okay, so most of the talk is really about classical Lagrangian classical theory, and okay. So just to make the connection with what we're going to do, I'm going to do in higher dimension. For the Lagrangian, the flow equation for the Lagrangian is by definition this one. Okay, so the derivative of this with respect to a parameter we usually call tau, p, or lambda, or whatever, is equal to the determinant of the stress energy tensor. Then we know that once you know the Lagrangian, the stress energy tensor is defined in this way through the Lagrangian. So this is the standard definition, but you can also use the Noether definition for the stress energy tensor. Okay, so you have this pair of equations, and you can carry on, for example, in a perturbative way to find the Lagrangian starting from an initial condition for the Lagrangian, and usually you can resum, and there are other ways, for example, the one described in the work by Bonelli, where you can find an exact, you can solve directly the flow equation by replacing the second equation into the first. Okay, and so what is it? It is interesting that in general, the first discovery of the form of the Lagrangian came from example, simple example like free boson theory, and in this case, I add the potential is not changing much. So L0 is this one, and the potential is generic. The important thing is just it does not depend on the derivative of the field. Okay, so then you solve the flow equation and you get this famous Nambu-Goto type Lagrangian, and this tells you that there is some connection with string theory, with simple model of string theory, and I think a big part of our community was really interested to the connection with string theory. And okay, so this Lagrangian as you can see, it's quite complicated. There is a square root. There is, in general, a non-vanishing potential inside. This tau bar is defined in terms of the old tau, and it's potential dependent. But a nice fact that would be relevant for the following discussion is that if you calculate the equation of motion using this Lagrangian, then through a change of variable, a dynamical change of variable, you can reduce the new equation of motion that are complicated because they will contain square root and things like that. With this particular change of variable, they will be reduced to the original equation of motion. Okay, so to be more explicit, if I define this change of variable to this through this Jacobian or inverse Jacobian matrix, it's not really important. So here you have the potentials, and here you have the kinetic terms. Then if you solve this equation, let's say W with respect to Z or vice versa, then the main claim is that the solution, okay, so suppose you have a soliton solution or a particular solution of your original equation, you modified it by changing the value, by increasing the value of tau, then the main claim is that the solution of the perturbed equation of motion is equal to the solution of the unperturbed equation of motion, but on Curly coordinate, and the Curly coordinate would depend on the field configuration itself. Okay, so it's very complicated, but you can form this change of variable, and this is what I said. That's a very complicated equation of motion. You perform the change of variable by integrating this Jacobian relation, and you go back to the unperturbed equation of motion on the W variable. Okay, already at classical level, this has very interesting consequences. So for example, if you study sine Gordon, you can study soliton solution and find immediately, or not, it's not too difficult, let's say, to find solution for the perturb TT bar perturb equation of motion. So for example, this is the standard breeder. It's a soliton anti-soliton bound state, which is breeding, so in time, which has this form. If you increase tau, it's become fatter. It's like it's growing in dimensions, while if you go to negative tau, then it's shrinking. It's like diminishing dimensions. Okay, so this is a quantum analog. This is the rod, hard rod type deformation that was mentioned yesterday. So essentially, if you start from, or there is at least an interpretation which at quantum level, if you start from a point like particle, then for positive tau, it becomes larger. It will become like a rod, a hard rod. It's taking more space than a point. Okay. So I think these are really the beautiful facts about the TT bar in two dimension. We understand more. We know the exactest metrics. We know how the spectrum evolve. All the quantum spectrum, finite size quantum spectrum evolve, okay, through this Burger equation. Okay, so let's be more general. In the general case, this Jacobian transformation or Jacobian matrix can be generically replaced with this one, which depend on T bar and half of the trace of the stress energy tensor. So in general, we don't need conformality. So the theory shouldn't be massless. But what the last important fact I want to borrow from two dimension is that once you know the Jacobian and you know that you are moving from, let's say, orthogonal or straight coordinate or Euclidean coordinate, whatever, to curly coordinate, then you essentially are changing the metric. Okay, if you know the Jacobian, then it's very easy to derive the form of the metric, and this is the form of the metric you get. So this is the metric. This is the deform metric. Of course, when tau is equal to 0, you go back to flat straight metric. And on the right-hand side, you have the right-hand side is quadratic in T. Okay, this is one point, and the other point that the indices lowering and moving up and down the indices on the right-hand side is done using the flat metric. Okay, so this tell us that this is a sort of expansion of the metric around the flat metric. Okay, so it's we will recover this result in a more general setup in which we will deal to higher dimension, to theory, to PT bar like perturbation in higher dimension.
I have a question. Maybe this question is not relevant to your talk, but I just curiosity, like, people talk about the root PT. So is there analogous approach, like change in metric?
Yeah, I think Christian already replied last time, but I didn't. I don't know the paper, but it looks as there is no change of variable. Okay, so but there is a change of metric. Okay, is it? So I think change of metric is more general. So having a change of variable, it means that you are not changing the curvature of your metric. So it's asking too much if you go, for example, up in dimensionality. So the purpose is to try to generalize this classical setup to higher dimension and look instead for a change of metric. Okay, I mean, demanding that it is a change of coordinate, a dynamical change of coordinate is too much, is too restrictive. So it would happen only if you do some dimensional reduction, like scattering of two plane waves, an infinite plane wave, or something like that.
So that means that there is some change of metric which cannot be explained by change of coordinates.
Yes, exactly. So that's the main point. So we can forget. I mean, this is essentially due to this problem here, because in two dimension, this puts you a relation between one derivative with another derivative. The sum of the two should be 0. Here, it's if you go to 3 dimension, you have 3 objects, and it's not easy to construct something which, for example, give you a Jacobian, which Hessian is symmetric. Okay, so this is just the statement. Okay, so just to tell you that 2 dimension is very special, and we cannot expect a priori to find such nice property in 3 or 4 dimension or higher dimension. Okay, and a bigger problem is probably the fact that in higher dimension we don't know how to quantize the theory we will obtain. Okay, so it's a big problem, but it's a problem, as we know, related to the fact that these perturbations are irrelevant. Okay, so let's move. I mean, with this idea that we are looking for something similar to the metric, so we obtain in 2 dimension, forgetting about.
If we move on to higher dimension, can I ask one more question?
Yes.
So we can have also other higher energy momentum tensor, TS.
Yes.
For example, T2 is a T square basically, right?
Yes.
And can you do the same statement that can you absorb this deformation into some kind of metric transformation or coordinate transformation?
Okay, so there are other cases apart from TT bar where you can find the metric and the change of variable, things like that. But they usually spoil if you use T2 or T3 or whatever. Then you usually have to break a Lorentz invariant. Okay, so it's essentially the propagation, the time, so if you have a higher conserved charge, the time is not the same time of the original theory. And so you are moving, for that reason, you are spoiling, automatically spoiling Lorentz invariant. Okay, so this is really borrowing and generalized what we had in 2 dimensions. So the main difference here is that if I want to speak about a theory with a background metric, which is in general non-trivial. Okay, so this is a general analysis, and I start from a background metric, and then essentially what I'm going to do is to try to see how TT bar deformation, TT bar like deformation would evolve this metric with tau. Okay. Okay. So this is identical to the flow equation in 2 dimensions. I just introduced the metric as usual there, and I'm going to deal with this operator here, which is a generalization, one of the many possible generalization of the TT bar operator in higher dimension. It reduced to TT bar in D equal 2 when R is equal 1. Okay. And then together, so with this definition and the flow equation, I need the standard definition of the stress energy tensor. And then this equation plus this will close up, and in many cases you can solve and find the perturb Lagrangian. And we know, for example, that the Bohr-Eiffel it's related to Maxwell through TT bar-like perturbation. In that case, I think R is equal 1/2. And D is equal 4. Okay, so these are the definition. Then it's I think it's good to write this perturbing operator in this form. So we introduce this T hat. We originally called it T bar, but we thought it was a bit confusing. So we call it T hat. And T hat, it's related to T through this equation here. So the second equation here on the left. So it's related to the trace of the stress energy tensor. And there is this, well, if you want to write it in a compact way, there is this function f. And this f here is defined here on the right-hand side. Okay, it depends on this parameter r, which is the same r which is in the original definition of this perturbing operator. Okay, so one family.
In the previous slide, I wanted that in general we can add one more free parameter in front of the trace of T square. But is there a reason that there is only one free parameter R? Or?
No, yeah, actually, yeah. I think at the beginning we fix this parameter to the one which would give naturally the Bohr-Eiffel starting from Maxwell. Then we realized after the first version was out that there was more freedom that I will explain now. And maybe, yes, you have the possibility to add the other terms. And that would be, maybe we can discuss, I think it's important. It's important to make connection, for example, for the effective field theory describing photon scattering, which are effective field theory that you can get out from QED. And so I think with one parameter I cannot match the standard result, so it would be important to add another parameter. So, for example, I would guess that you can always add something which is proportional or to the action to the Lagrangian square or something like that. I'm thinking, but if you have a good idea, then we can try. Okay, so it's defined in this way. So R is the same parameter, and then the first step. So I'm going to work a bit Cardi so infinitesimal variation. Okay, so the flow equation I introduced before, I can just write it in an infinitesimal form. So delta tau, and this is it's equivalent to the previous one, but I'm now working without using derivative. So delta tau is really corresponds to infinitesimal variation. Okay, so this is the original flow. And now let's take an alternative point of view. Also, this can be deduced a little bit by from Cardi work, okay? Which is the following. So let's take now, I think the convention of the argument is a bit strange, but I didn't have time to correct. So let's now take a new action, which depend on this H, which is can be interpreted as a deformation of the metric, but anyway, you can consider it as an independent variable, independent field, written in this way. Okay, so you essentially add something like the square of the matrix, which sounds a bit like a massive gravity, and maybe there is some deep relation. So it's still, has to be totally investigated. Maybe somebody will already working on it. Okay, so if you expand this for smaller tau, then do it to the definition of the stress energy tensor, so you can equivalently write it in this way. Okay. Okay, so H hat depend on the field, let's say phi field. Okay, the matter field, for example, and then on this H here. So what we can do, okay, and the other point, there is this epsilon here, which is similar to F, but with another free parameter. So this is how we manage to increase the number of free parameters. So it's defined in this way. So there is a new free parameter Q there in the second definition of the action. And so the difference between E and F is given here on the right-hand side. Okay, so let's take the second action, take a variation. So try to find the equation of motion for H. So let's take variation of A with respect to H, and this gives you a constraint. Okay, so this gives you a constraint, so a relation between H and the stress energy tensor. Okay, so you can write it in this way. So this would be the star just means that it's solution of this equation. Okay. So this seems to be a completely different theory for not that expert. So it was also new for me. But we can require that the equation of motion of the two actions, so the first one and this A hat, are equivalent from the point of view of the field of the phi. Okay, so the idea is the following: that we can try to match the derivative of the first action with respect to the field phi, set it equal to the derivative of H8 with respect to phi, and then fix so. Keeping free H here, and then fix at the end H equal to X to the solution of this equation of motion. Okay, is it clear? Okay, so you do that, this is equivalent to that, and then only at the end you fix H. Okay? And so this gives you the same equation of motion for this field or matter field or whatever you want to call it. Then are the same equation of motion, and we indicate that, I don't know, maybe there is another way, more standard way to indicate them, that this means that this action here on the left-hand side, which means is dynamically equivalent to the action on the right-hand side. So in the sense that the equation of motion are the same. And remember that the equation of motion of this at you first derive with respect to the field, and then you set H to the solution of the equation of motion. Okay? So the procedure is that. So it's an infinitesimal move, and then you have this. You calculate this the derivative. Functional derivative, and you try to match so the two results, and you can do that, but you need to fix a relation between the variable c, the variable q, the dimension, and the variable r. Okay, so if you fix c to be this value and q to be this value, then h star becomes linear in t hat. Okay, a very proportional to t hat, a very simple expression. Okay, so at this point, the main claim is the following: that the two actions are dynamically equivalent if the matrix satisfy this flow equation. Okay. Okay, this okay, so this is the statement. This deform action, tau plus delta tau, with the ground metric G tau, which is here, is dynamically equivalent to the theory A tau with the deformed background metric at tau plus delta tau. Okay, so this is the statement. It's a sort of reabsorb the perturbation from the equation of point of the tau perturbation from the equation of motion point of view by changing the metric. Okay, I think it's Polyakov, applying Polyakov idea somehow in a hidden way, probably. Okay, so equivalently, we have this flow equation, which a little difference here, and I think we will use this with the positive sign. Okay. Okay, so the first question, the important question is, so I have this perturbation. This perturbation is equivalent to a change of the metric in your system. Is this metric, so if I start from flat metric, like in the Maxwell equation or even Borg-Infeld equation with flat metric, if I do this, so I increase tau and then reabsorb the perturbation in the metric, is this deformation of the metric, is the new metric, is the deformed metric still flat or not? And so you can, starting from flat metric, then you can simply do the calculation. Okay, so this is first order perturbative calculation of the Riemann tensor over flat metric, flat Euclidean straight metric. Okay, so the result is the following. It's of course proportional to delta tau, to the perturbation, but it's non-trivially vanishing. So maybe again, as I said, for some configuration might vanish, but is not in general is non-vanishing. So so this already tells you that outside 2 dimension, okay, the curvature is in general of the metric is in general changing. Okay, so out of this, by contraction, you go to the Ricci tensor, and also this is non-vanishing in general, and then further contraction give you the scalar curvature, which now can vanish. Okay, so because you have this factor here, we depend only on the parameters that you have. So depend only on D and R. So you can set this quantity in parentheses to be 0, and then you would have a 0 scalar curvature. Okay, so if you do that, then delta R is equal to 0 is R is equal 1 over D minus 2 minus 1 over D minus 1. So it means that when D is equal to, the scalar curvature is 0. Okay, and then since in D equal to the Riemann tensor is only one independent component, then this means that you start from flat space into dimension, you carry on having flat space. Okay. Okay, so this is explaining a classical, let's say, classical argument in general why two-dimension is spatial in this respect.
Ask, so this is the condition for the.
5 minutes.
I'll on quickly, sorry. This is the condition for the scalar curvature to vanish. Do you get additional conditions by requiring that other curvature invariants like RAB, or the square of the Riemann curvature vanish?
We didn't try.
You did.
Okay, so in 5 minutes it's going to be tough. Okay, so we have then one flow equation involving G and T, and this is to close the system, we need also to have a flow equation for T, and it is not easy. It's not difficult to find because it's hidden in the flow equation for the action. So you take the flow equation for the action, you derive it with respect to the metric, and this is what you get. Okay. The other point that here you have a partial derivative with respect to S, and we would like to have instead the total derivative. So you use this second expression there, and finally you find a closed system. Okay, so you have derivative of G, and here you have a total derivative of T, and you can close the system. Okay, so this system is very nice because allows you to start from, for example, from Euclidean metric and perturb do a perturbative expansion of the metric on your flat background. Okay, so and these are the coefficient here, alpha and beta. They are related to trace of T over trace of T squared. Is it okay? Okay, so suppose that now we have this exact flow equation, you need to solve them. Okay, you can do it numerically. We use another approach. We would like to see, the face of the object. Okay, so this is some statement. Maybe it's not so important. They are not so important at this stage, but what is important that we perform a perturbative expansion around the flat metric, which we describe in this way. So the E are the field bane. Okay, so okay, so the idea is the following: you assume that the metric can be expanded in this way around the flat solution. Okay, so the flat field bane, for example, or the trivial field bane, and then you plug this expression in the equation we had before, in the flow equation connecting G, E hat, and the flow involving only T hat and the metric. and you get a recursive system which can be solved perturbatively. It's really a general formal calculation. It's really one line of mathematical code, and it in 2 minutes can give on a laptop can give you 10 terms in the expansion. So these are the first term in the expansion. Okay. So on the right hand side, everything is evaluated on the flat metric, a bit like what we saw in 2 dimensions. Okay. Now we like compact form, so we like truncations. So the first thing we did is to try to solve the system and to impose a truncation, general truncation. Okay, so that would depend only on the property of a general property of the stress energy tensor of a specific theory. And what we discovered is that if this property are true, so if the eigenvalue of the stress energy tensor matrix are somehow degenerate, then you have a truncation. Okay, so in our dimension they must be heavily degenerate. So for example, in 3 dimensions, in all dimensions, all the eigenvalues should be equal. So I don't know any system, but if you have any idea with such a huge degeneracy. But if you go to 2 dimensions, there is no constraint. In 2 dimensions, the eigenvalues can be can be independent, and you always have truncation. And we know we have truncation for PT bar, for example. Okay, and then okay, so actually this is true only in specific case, but anyway, degeneracy. So when you have this expansion in tau hat, the degeneracy means that the higher order can be written in terms of lower order terms easily. Okay, so the first case, compact expression we had fulfilling this property is the case R equal 2 over V. Okay, in that case, the resulting metric is the following one. So it's linear. It's even better than in 2 dimensions. So it's linear in T hat. Okay, it's linear in S. And you see, if you go to and you have a power this 4 over D. Okay, it's a very simple expression, but you still have this power 4 over D here. So if D equal 2, this has become quadratic. Sorry if I confused you before. So if D equal 2, this is quadratic, and you get back to the original result in 2 dimensions. If D equal 4, it's even simpler. Okay, for the space-time dimension, it's even simpler. So because, as I said, I wanted to say before, it's linear in T. Okay, and then if you differentiate this, then you can get the exact T hat equation, which give you also the exact T mu nu. Okay. So if we look at 4 dimensions, there is a particular wide family of theory in which the condition is fulfilled, the degeneracy condition is fulfilled, and this contains the Maxwell equation, which you can perturb and give you, for that value of R, you can get the Born-Insel equation. But in general, you have truncation for any abelian gauge theory in 4 dimensions. So this is also true for the mod-max equation. So you can have a Born-Insel version modification of the mod-max equation. And then this is, just to conclude, I think this is the things maybe we should look at too. So there are experiments, they are using effective field theories to probe, to understand photon-photon scattering. Okay? and also birefringence. So when you your photon, your plane wave or laser wave moves through a strong magnetic field, you might expect, since you break the symmetry, you might expect and it's the refraction index. You expect that the refraction index to be different in the orthogonal and in the parallel direction. Okay, so Bornfeld, as we know, the standard predict photon scattering, but it predicts a change of n, but zero birefringence. Okay. While the mod max predict a non-vanishing birefringence, and this birefringence and of course photon scattering are predicted by QED, quantum electrodynamics. Okay, so maybe we should have a look. So one of the problems here, if you do, the effective action you get from QED is slightly different from the effective action, at least the first order. It's important for this type of calculation is different, slightly different. There is a coefficient which is mismatching, which has a mismatch with compared to Bornfeld. So maybe putting Bornfeld with mod max will cure the problem, or maybe we need some other. I think this high degree of freedom, as far as I can tell, is probably not enough to fix this problem.
So this is Padova group is doing the experiment?
Sorry?
The Padova, you say this.
It's a concrete experiment. Yes. Yeah. So they put an upper. So
There's some upper bound.
Yes, there is an upper bound. So this parameter in the mod max Lagrangian is usually called, I don't know whether it was called gamma or eta in the previous talks. That should be very, very small, but it's proportional to the magnetic field. So if you increase really very much the magnetic field, the birefringence to the phenomena should become stronger. Okay. Well, just to conclude, another case where we can resum, so there is no truncation, but looking at the coefficient of the expansion, we could really read what kind of function was in total. We could resum the case also R equal 1 over D, and this is giving an exponential. So this, for example, if you go to 4 dimension, it must be related to some other change, some modification flow related to different from Bornfeld, but maybe it's very interesting to study. And so we only managed to study the one boson case, and this is the Lagrangian. It's very complicated, and it's involving this Lambert function. Okay, and the Lambert function is actually this combination is involved in this counting of level 3 with n vertices. So this is essentially the generating function. Okay, so I think I can conclude that meanwhile, there have been important progress. So in this paper, using characteristic, the method of characteristic, the same equation for the flow of G mu nu was obtained. There is also a compact form for the metrics, but I don't think explicitly you can do very many calculations. But I think, again, this is an open problem, and both Joe and Asa should try to understand the connection between this expression and the perturbative expansion. It's very tempting. I mean, it's a very nice expression. And then, there is the emergence of TT bar, of root TT bar, and we already heard about this theory. Okay, open question, relation with the massive gravity. So generalization of this JT duality in higher dimensions and generalization to non-relativistic deformation. Okay. Thank you to the organizer for the organization of this fantastic meeting and for the invitation to speak here. It is always very nice to be here in Korea. And the first time I was here, it was about 25 years ago, invited by Chandrin, and then we spent a beautiful time. Okay, so essentially, I'm going to work to talk about the work in collaboration with these people. So Gianni, Francesco, and Stefano, it's about the study of an harmonic oscillator, a particular one which is essentially related to the TT-bar perturbation and to other interesting mathematics, like, for example, it's closely related to the study of things, involving the zeta-Riemann hypothesis, and in particular the very Keating Hamiltonian. Okay, so
Can you click the slide?
yes.
You click, and then after that.
Okay. Okay, so first of all, a very short, brief recapitulation of the property of the zeta-Riemann function. Well, you all well know that it appears in many branches of physics and mathematics. It's related to prime numbers and things like that. So this is a serious representation of a Riemann zeta function, and I'm not going to say much about the zeta Riemann function, apart that at a certain stage it's important that it fulfill this functional relation. And then the analytic properties are also quite well known. So there is a singularity, a false singularity at s equal 1. There is a series of trivial zero, which are on the real axis, on the negative part of the real axis. And then there is what we call a critical strip, or what is called a critical strip, which is essentially starting from 0 to 1. It's this vertical strip where all the zero of the Riemann function are supposed to be. Okay. So the Riemann hypothesis is constraining more the zero of the zeta function in just saying, so the claim that the non-trivial zero are located exactly on this critical line. Okay, they appear always in pair because there is a symmetry in the function. So an object which will be important in the following is what is called a counting function. So are you all familiar with zeta Riemann function? Yeah, you are. Okay. So is the counting function. So essentially comes from Cauchy theorem for what is called argument principle for meromorphic functions. So this is the definition of the counting function. Also essentially is counting the number of zero minus the number of pole in a given region bounded by this curve gamma. Okay, so it's trivial result of a complex analysis. Now, to define the counting function for the Riemann zeta function, we just look at the non-trivial zero here on the critical strip, and we choose a contour which is something like this, so a rectangular in the upper plane, upper imaginary plane, positive imaginary plane in this way. So we integrate, and since we know that there are only zero inside the strip, then we can define this n, which is counting exactly the zero. Okay, so there is this parameter, which is essentially the height of this rectangle, and we define through this count. Okay, so one important result is that we can, using the functional relation for the zeta function, we can split the counting function in two parts. So this is an important observation. It will be very important in the following. So there is a smooth part of the counting function, which is related to this the Riemann-Siegel theta function, which is defined simply, is a simple object, is defined as a ratio, log of a ratio of gamma function, is defined in this formula. And then there is a no-smooth or oscillating part. Okay, of course, a counting function is something like a staircase function, so it has a steps and jump. Okay, so this is what I just mentioned. So the total counting function can be split in two parts. This is the smooth part. We can think about it as the average of n of t, and then we have a fluctuating part. Okay, so the smooth part fits very well inside, the fluctuating, the total counting function. Okay? So it's anyway a good approximation, and it's not predicting at all where the zero, the Riemann function are, but it's an important ingredient. Essentially fix the asymptotics of n of t. Okay, the other important fact, I'm going to do a lot of WKB and high-order WKB on a simple quantum mechanical model, try to first of all, try to match this series of the smooth part of the Riemann function. Okay, so asymptotically, the smooth part grows like t log of t. So this times this, then the subdominant term is grows like t. And then there is an important bit, which is this constant, 7/8, which for example, for the harmonic oscillator would be 1/2. So this is a different number. It's characteristic of the smooth part of the Riemann of the counting function. And then there are subdominant terms that go like the inverse power of t. Okay, so t is some sort of energy parameter. Okay, so you don't need to remember much apart from that there is t and then a log of t here -1, there is this 7/8, and you can maybe remember also, keep in mind this 48, this 7/5760, etc. So I'm trying to reconstruct using some sort of nonlinear harmonic oscillator this whole series. Okay. So it's a smooth part, so it might come from WKB analysis of a system. Okay, and indeed, everything, all these ideas are very old. They come from the Hilbert-Collier conjectures. So the Hilbert-Collier conjecture just say that you might be interpret or think to interpret the zeta Riemann function as a spectral determinant. So some object which contain information about the zero, about the eigenvalue of a certain operator, a self-adjoint operator. So if you can prove that zeta function, it's if you can find a self-adjoint operator which has the zeta function, you can eliminate all the trivial zero and the poles to make it an entire function. If you can find an operator, self-adjoint operator, then we know the spectrum is real, and we essentially prove the Riemann hypothesis. So it's another way, it's a more physical way. So this is why many physicists wants to work sometime, and maybe when they are my age, old, they don't have more important things to do. They play with a little system, a simple system. Okay. So then, Barry Keating, much more recently, but at least for me, I mean, had a paper 99 paper had come out with a speculation or a conjecture. So there is essentially this sentence in the paper. So the Riemann dynamics is related to the trajectories generated by the classical Hamiltonian P times Q. Okay, P is the momentum and Q is the position. So it's a very simple, it's P times Q. It's a very simple system, but if you look at it, it looks, it looks immediately wrong. I mean, how can it be possible that something P times Q, which has no bounding potential, nothing, might have a spectrum which is a discrete spectrum. And so the other problem, so how is it possible that such a simple object might be related to the Riemann hypothesis? Okay.
What is Riemann dynamics then?
Sorry?
What do you mean by Riemann dynamics?
Well, essentially, yeah. Okay, I'll explain. So for what I understand, this is essentially the claim. So the Barry Keating essentially claim is that the non-trivial zero of the zeta function corresponds to the eigenvalue of some hypothetical quantum version of this classical Hamiltonian. Okay, so we need to quantize this object P times Q, which is a trivial object classically, but essentially it has some peculiarity, and we need to quantize it. Okay, so it means at a quantum level you might have correction, non-trivial correction. You can add left and right object would cancel and commute, and so people is working on that type of generalization, that type of Hamiltonian. Okay, but the very strange fact. Okay, first of all, I mean, it's Keating. It's Barry and Keating, so we cannot just say, okay, well, it's rubbish. I mean, it's very deep. So there must be something in it.
What was the original motivation? Like, what is the motivation to say that?
Yeah, I think it's an observation. Okay, so in this paper, they did a lot of stuff, also numerical stuff related to the zeta function. And then in the final part of this paper, there is this proposal. Okay, so it's really, strange. Yeah, very.
There's some advantage to working with this rather than just the harmonic oscillator, like P square.
Well, the harmonic oscillator spectrum is completely different from the Riemann.
It's like a harmonic oscillator Hamiltonian with an I or something, right? It's just a dagger kind of Hamiltonian.
Yes, exactly.
It's an advantage.
Well, it's not the harmonic oscillator. So if you do the rotation of the variable, so canonical transformation, what you actually get is the upside down harmonic oscillator, which is non-confining. They would have the same problem as this one. But let's not move from this. This is problematic because while the harmonic oscillator would have bounded and closed trajectory, in this case, we don't have closed trajectory. Okay, so I'm talking about classical trajectory in the Q plane, in the configuration plane. Okay, so to see that, let's look for the curve where P times Q is equal to a constant, let's say a fixed energy. I mean, they're classical trajectory. And then they are hyperbolated, so open, so they go from minus infinity, from plus infinity to on the horizontal axis to infinity on the vertical axis. Okay?
Q cannot be negative?
Well, okay, you can you repeat this on the 4 quadrants, but still the trajectory will be open. So it's not a closed trajectory. There are no bound state in that sense that we think about the harmonic oscillator or anything that might have a discrete spectrum. Okay.
Energy is also not bounded below.
Sorry.
The energy is
The energy is not even bounded from below, and indeed that this is the signal that you have open trajectory. Okay. Okay. So how they solve the problem? So essentially, they introduce a sort of they cut the trajectory in a particular way.
Can you click on it? So it's like the trajectory. Yeah. Now we can use it. Yeah.
Okay. In this way, so they stop the trajectory in here. So this distance, let's say h bar is equal 1, and this h bar is equal 1 in this picture. So this is the elementary Planck cell, square root of 2 times pi. So they interrupted the trajectory at this point. At this point, I think probably they close the trajectory in this way, but that's not important for the following consideration. The important part that now the area under this black area here, you calculate it, is giving you, you divide for the unit cell, and it's giving you the leading WKB approximation. You can do the integrals. It's very simple, and you get exactly the asymptotic of the smooth function, the leading asymptotic of the smooth function. Okay, so in their paper, they also mentioned that you can include the 7/8, and this is related to what is called Maslow index. It's related to the deflection angle around the trajectory. So I didn't do this calculation, but let's say it's not important, and you can question this point. I mean, this is a classical trajectory. Why, for example, the harmonic oscillator, the 1/2 is coming from quantum correction, so it's a quantum phenomena. So it's a bit strange, but I think this is based on standard of, number of observation, which tells you that there is a relation between this deflection angle and the Maslow index. Okay, so and then apart from this classical semi-classical analysis, no one really knows how to go further than this. There is an alternative proposal, which is more or less equivalent, is by Connes. So, the idea is very similar. You put a cutoff in P and Q, but a fixed cutoff lambda in this way. And then if you calculate the area of this one, and you divide by unit Planck cell, then you get something which is similar. There is a cutoff dependence. So when you send the cutoff, everything goes to infinity because the trajectory are open. And then you have this leading asymptotic, but with a different sign. Okay. So this is, if you can do something which is doing the complementary things to compare to what you want, is not a big problem. Okay. So it's the physical explanation that they have this absorption spectrum compared to the standard emission spectrum you might have in an atom or in the harmonic oscillator. So there is a beautiful review by German Sierra about this. He's working together also, I think, with other people like Moussard or Leclerc on similar related stuff. Now, why I'm interested in this? Well, it occurs that Gianni Coppa is a professor at the Polytechnic in Torino, but he's an engineer, but decided to study also to take the degree in physics. So he asked me a thesis, and I gave him a thesis on the Boring-Infeld and TT-bar. And he had the idea to understand the property of TT-bar perturbation doing again a dimensional reduction. So the dimensional reduction scheme is using, he will introduce, is that at first a discretization. So this is essentially the Nambu-Goto Lagrangian, and is discretizing it along the space direction. So you move from integrals on this infinite sum, and the discretization is made in this way. Okay. And then by changing name of the function, then he arrived for a single oscillator. So the simplest case is a single oscillator. Here he arrived to this expression here, which is probably not what we expect from TT-bar perturbation of quantum mechanics, because here it's the full Lagrangian. Sometimes you see, so there is the derivative part plus the potential, and usually in TT-bar, maybe the potential it's apart from, split from the derivative part, and maybe in one dimension you expect to have not have the square root, but maybe a pole instead. So something like h over 1 minus tau h. Okay. Now what you do is a standard. We want to study this model at the level of the Hamiltonian. So you define the canonical momentum in the standard way, this one. And then you introduce a parameter. We like to have a flow equation. So we
I have a question. So where does Q square come from? And inside this.
Only one track.
Okay, going up or down?
Yeah.
So you can see it's coming from here. Okay, so only one oscillator. So you fix, let's say, this 0. This is 0. This is okay. This is non-zero. This is 0, and this is not. So it's like a chain of oscillator. Only one survive in this chain, and so you get the 1/2 phi square from here, 1/2 phi square from here, which is reconstructing this. Okay, it's I wouldn't have done it this way, but he did, and I think it's a reasonable, acceptable way to dimensionally reduce the system after discretization. Okay, I have to be careful with this. Okay, now we rescale the field, we rescale the Lagrangian, or this is the Lagrangian, yes. We rescale the Lagrangian, introducing this parameter that usually we call T or tau in the TT-bar flow. And we do the Legendre transformation, we go to the Lagrangian, and this is what one gets, okay? So this is the Hamiltonian as a function of P of Q. This is classical Hamiltonian. Now you plot this Hamiltonian and you see that it has, let's say, the potential as this shape. And so the trajectory, they are not the harmonic oscillator trajectory, so they are approximated circle in the middle, but then they are deformed. And then they are deformed in the way the very heating Hamiltonian would have a trajectory.
But epsilon going to 0 it just become the simple harmonic oscillator.
Yes, exactly.
And then
so when epsilon is going to, so this is a deformation, let's say a TT-bar-like deformation of the harmonic oscillators. When epsilon goes to 0, you go back to the harmonic oscillator. Then at finite epsilon, then the trajectory are the form at large energy, and they have this detail. So surprisingly, this Hamiltonian is putting in a natural way a cutoff to the repeating trajectories. Okay, so one important fact is that let's say in the PQ plane, the initial rotational symmetry is broken and it remains a Z4 symmetry. This is important, but because when you do calculation, you always end up with 4 independent sectors. Okay, so we did truncated space and manipulate before numerics, and you have the splitting, so they are separated. There are 4 separated sectors in the theory. Okay, so we needed essentially to get first some information about the eigenvalue of this Hamiltonian, and the first things we did, which is not completely correct, but it's giving you some estimate of what's going on, is to take the square essentially of the initial Hamiltonian, eliminate the square root, and produce a new operator which we call kappa. Okay, so the idea, it's a bit like a mean field approximation, is to study first the spectrum of kappa. Yeah, with the method you want, WKB or truncated space approach. Then take the square root, assuming that this is good, it's okay, in this kind, also quantum level, and you get the good behavior. So what we check is that you can do this, but it's it's an approximation. So the two methods, they differ at high order in the perturbation theory. Okay, but qualitatively, it already tells you what's the behavior of the energy levels. Okay, so here we are at epsilon positive, and you see this is the harmonic oscillator point. So the levels are evenly spaced and they are smoothly deformed. We don't know. But so they are smoothly deformed, but we don't know exactly, of course, how they do. But again, the different color means that there are 4 different sectors. Now, if you take brutally the square root of this result, this is what you get. Okay, so
numerical region, numerical.
Numerical, I think Gianni did I think a program in MATLAB. And
I think that it's truncated. Means,
yeah, it's truncated. So essentially, you have, and then you go on the basis of the harmonic oscillator. You calculate the big Hamiltonian or the big kappa matrix, and you diagonalize it. I think it's quite a standard procedure in perturbed conformal field theory when people talk about truncated space approximation.
For instance, like hit some like a harmonic oscillator, observe some Hilbert space, there's some cutoff there, and within that.
Exactly.
Okay.
So you have this big matrix, and you diagonalize it, and so it's a non-perturbative approximation, but it's still an approximation. Okay. So, and this is what you get, which it's very nice. So here again is the harmonic oscillator limit. The levels are very smooth, so there is no problem in doing numerics. And of course, still now you have a square root, you have doubling of energy levels, and they at epsilon go to 0, they are disappearing, they go to minus infinity. So it's very similar to what's happened in the standard TT bar perturbation. Okay.
What are the 4?
So the Z4 symmetry means that, for example, red, and they are the couple. Okay. So you can think about a subsector of the theory, like just taking the first level, the fifth level, et cetera, independently from the other, because the perturbation is not coupling them. Okay? So and this, you know, you can see it from even from the classical trajectory. I mean, that force symmetry survive. Okay, so now you do WKB. Okay, on this, so it's automatically regularized, so the trajectory are closed, so we expect a discrete spectrum. Okay, the first calculation, WKB calculation, again, it's related to the area in the phase plane. Phase space plane, and you do this calculation, and essentially you can write in terms of elliptic complete integrals. So at first order, it's very easy to perform this calculation, and then then you have to go further, and what we use is the Weil quantization. So essentially, it means that you expand this Hamiltonian with this square root. It's an infinite order differential operator, okay? And then you use the Weil symmetrization, and there is an algorithm. It's a very well-defined algorithm. It's slow to implement it mathematically, but we manage with time to get many results. Okay, so our first order is this. We need also a second order, because if you want to understand what are the coefficients in this n of t, so leading, subleading, and subleading, so the constant term, we need there is some mixing, because these are non-trivial function, non-trivial polynomial or non-trivial function. So second order, let's say in H bar, this is essentially the quantization rule for this. So on the right-hand side, you have the standard quantization rule with n plus 1/2, and on the right-hand side, where you have this complicated stuff, but involving only elliptic complete integrals. And the relation between we fix the relation between Qn and En. En are the eigenvalue of our problems in this way. And then you do an expansion. I mean, Mathematica is doing very quickly the expansion of this elliptic integrals. You get the asymptotics, and it's a mess because it depends still on H and epsilon, etc., etc. So we fix, without losing generality, we fix H bar equal 1. And then we notice that for this value epsilon, which is non-zero, of course, and with this choice, so this question mark whether you have to correct this at higher order, but you fix this relation between Qn and T, okay? And then you choose a particular sector for n, so it's multiple, 4 multiple integer times 4, and what you get is this result. Okay, this comes essentially because of this choice. So choosing a subsector which is a multiple of 4, you essentially divide by 4. I mean, putting 1 on the right hand side and divided by 4, you get essentially this this term. Okay, without thinking about angle or deviation of the trajectories. Come naturally, but maybe it's not the right procedure. So I'm here. This is an informal talk. I'm telling you what I know and what I learned by studying this problem. Okay, so second order WKD on H bar, you get the correct leading, okay, subleading and subleading, which is the 7/8, apart from this question mark whether this is the right thing to do or not, but also this term here. Okay, So it looks as there must be a way to reconstruct the full smooth part using this, of course, using WKB, you will never get the oscillating part if, provided they are really, the no smooth part is really described by the Bender-Keating Hamiltonian, which is a big full mark. And then you have log correction, which in general, they are expected from the fluctuating part of the zeta Riemann function, but I don't know how to match. I think they do not match the oscillating part of the zeta function. Okay.
Can you explain again the identification 2 and T?
Okay, so if we fix, so this is an assumption. So we look at the final result, the asymptotic expansion, and we notice that if we fix this to 1 over 8 over 8.
In particular, Q and what was Q and
Oh, this is again, this is an assumption which simplify the final form. Okay, so if you don't choose, if you don't make this choice, then there are mixing and things look less related to the smooth part of the zeta function.
Oh, yeah, so can you remind me what was Qn?
Qn is the argument that came from this, they appear in these elliptic integrals.
But that was related to EN, energy.
Yeah, En, and now I introduce, it's a matter of change of variable to introduce another variable.
So T and EN relation is simple? Or?
Yeah, it's very simple. Yeah.
And what was N, capital N?
N, so N is counting the number of the position or the level, whatever. And then since it's split in 4, it's connected towers, I can choose small n to be 4 times an integer number. Okay, and I call it simply n because I'm now counting things through this n here.
It's a number. Okay,
yeah, it's a number, but if t is not n, so it's not tn because I missed here. So this would be the counting function. Okay, so it's a sort of the equation. The counting function, it's always defined in this way. Okay, so so I can get the 3 correction, even the sub leading correction here, which is 1 over 48. Okay, and then there are other corrections that maybe at a certain point they would be unwanted because we don't have control. So I don't understand from the zeta function how to get to the logs, and I would more expect some log square, log to some power instead of something simply linear in log.
Also, you also mentioned the 1 over t square in the function.
Sorry?
In the Riemann zeta function, you mentioned that this 1 over t square or correction.
Yes.
So number that doesn't match.
Yeah. So at this point, everything is matching up to this order. Okay. The smooth part. Yeah. Okay. The smooth part is this. The first term is this 1 over 48 is matching the expansion. So we can change the sign of epsilon. So we have good sign and bad sign in PT bar. Okay, so this probably will be the bad sign. So we change the sign. I mean, this is really not important. And now we look at the potential.
Just from the TT bar side, what is special about epsilon equal to 1 by 8 pi?
I don't know. Yeah, no, I mean, yeah. I think TT bar is, yeah, I don't know. I think for us here, it's special because it fits some result related to the zeta, to the smooth part of the zeta function. So it's the only, it's an observation. It's not, there is nothing deep okay, so now,
But if I just work with general epsilon, right? Like
for general epsilon, you can do for general. So we have the result for general epsilon.
Would that define,
but yeah, the asymptotic would be slightly different. And
would that define any generalization of the zeta function? Or is that...
I don't know. No. Yeah. Okay, so so if you plot now this potential, thing like that, what you get is this one. So the potential might become complex. So this here I'm plotting only the real part, and you see it's more complicated. It's maybe more interesting. So you have closed trajectory in the middle due to this well at the center, which is almost square-like. Square shape, so you have closed trajectory in the middle, and then here is unbounded, so you have open trajectory outside. Okay, so maybe this is the part relevant to the zeta function. I don't know, but on the other side, for epsilon positive, easier to do calculation. Okay, so what do we expect at quantum level? So we expect something which contain bound state, so some discrete level plus something continuum. Okay, and this was a bit a surprise. Okay, so we use the same numerical algorithm. So it's a truncated space, big matrices, huge matrices, diagonalization, and this is what we got. Okay, so this is negative epsilon. Okay, so you see that here, you know, the point. So it's a huge matrix, but a finite matrix. So you have some level, I don't know how to call it, whether they are not resonant. So they might be stable because, I mean, maybe the wall of this potential are too high to have tunneling. So these are the continuations. So here there is a little bit of positive epsilon. You see this level are continuation. This is the kappa Hamiltonian, and they carry on, and at a certain point they interrupt. It's you see, if you look carefully, they open. It's like they are spreading out. So you are almost have a line. So you, it's like the point they concentrate along this line when you do this truncated space, and then they spread up close to a line here. You can find it's analytically this is -1/2 epsilon, which fit very well the curve. And also, if you take your WKB and you do analytic continuation, you see that this level produced numerically, they are really fitting very well with the WKB result. Okay.
When you do this analysis, I mean, this is like you consider like the PMQ is an operator, but you consider some like a truncated space.
Yes.
Do you need this kind of ordering issue inside the scale root?
Yeah, it's the symmetric, it's the Weil convention, so it's always symmetric in the
between the scale root, you make it symmetric,
yes.
and then what else?
Yes. Yes. Okay, so it looks a bit strange to me because when we go to the bed sign, you think that you have only the level which become complex. Here, if you do numerics, so you have also this continuum level, so this continuum spectrum. So I'm not sure what the physics of it, but if I try to understand it in higher dimension. Okay. So if you open this line up, this is the result of WKB, but I told you this fitting very, very well with the numerics. This is what you get for H. So you have for negative epsilon, you have the standard square root appearance of square root singularity. I think only in the ground state survive if you go further and farther with epsilon negative, and for positive, this is the plot I already showed before. Is it okay? Okay, so then what we did is, you know, it was a very encouraging result. So what we did is to implement this Weil quantization scheme, which is very heavy. We use Mathematica. I was on a laptop and it took a long time, and you do it, and you see that the expansion contains all the smooth part coefficient terms, so all the terms related to the smooth part of the counting function plus a mess that we are unable to recognize. Okay.
The region, actually, I asked the 7/5760, that one, but the next thing.
The next is okay. So all these black ones are okay. So they fit the asymptotic expansion of the Siegel, Riemann-Siegel function.
From your calculation, you cannot observe this 7/5760.
So we can observe it's an analytic calculation. Yeah. So this comes from WKB. We did it analytically. Okay.
From the harmonic, the quantum mechanical.
Yeah, from the full, we call it Born oscillator. From the full Born oscillator, there is this, you apply this Weil quantization scheme, and you can get term by term in H all this contribution. Okay, so higher order WKB calculation, but there is this Weil scheme, which is well established. Okay, so what we get is the smooth part here. Plus this mess here that we cannot, you can say it's a mess, and what can we do about it?
One last question. So from this kind of expression, the Riemann point counting, how we can distinguish smooth part and?
Well, because the smooth part we know is coming from the Siegel Riemann function, the theta, which we know what kind of asymptotic has. Okay, so we split, but when you do the asymptotics, actually asymptotic expansion for this elliptic integral, then you get a lot of terms. So and usually the dominant terms are related to the smooth part. But yeah, it's to think a little bit, to have a look to the result is not really. Okay, but we were a bit surprised that even at high order we could identify inside this mess the smooth part of the accounting function.
So whatever is proportional to pi is unwanted, whatever is proportional to 1/pi is
Okay, so as I said, I don't know what this is. Really, if I don't want this, the red terms, but I need to put a minimal objective. Yeah. So the minimal objective at this stage, since this is coming a mess from this analysis, the minimal objective is to find a quantum mechanical system that would reproduce the smooth part of the Riemann zeta function. Okay, so this is the minimal thing, or the maximal thing I can do at the moment.
maybe what I mean to say is, like, since the good terms are like coming with the 1/pi and the dubious terms are coming with like proportional to pi, like you should be able to probably track it.
Yes, exactly. Yeah.
Because like
some
of the integrals give 1/pi. Some of the
it's not difficult to track it, but the mathematical output is not always easy to read. Okay, so the maximal, let's say minimal from the time, the maximal and minimal, whatever you want, whatever it means, objective is to find then an oscillator which has as a spectral determinant only the smooth part of the counting function. Okay, only it means that I'm proceeding with this type of WKB calculation. I don't know whether there are other contributions. So, for example, trajectory which move to other sheet in this Hamiltonian are really not allowed, or are they allowed? So I don't know. I mean, so the hope is that there is still something hidden in going in trajectory, in complex trajectory, like into this symmetry that can go, for example, on other sheet of the Riemann. Okay, so the minimal. So then we came up with this. Similar objects also appear in TT bar perturbation in higher dimension and things like that. This Bonelli et al. Paper. So we modified the this board oscillator in this way, introducing a parameter. This so this is I mean, to do the calculation, you need this to be an integer, and in particular, more precisely, it needs to be an even integer. So it's an even integer if you want to perform a calculation, WKB calculation. And this is nice because as you send P and Q to infinity, you get back again the Keating, the very Keating Hamiltonian PQ. But also formally, if you send U to infinity, you get the very Keating Hamiltonian if this is true. So because there is the power of U here and this root U here at exponent. Okay, is it okay? So it's a deformation of our initial model, but it's nice because you now have a new parameter you can play with, which is this. Okay, so these are the trajectory. Okay, so this is a fixed trajectory, and you increase U, the parameter U. So start from 2, which is this what we call the Bohr oscillator, and then U equal 4, 6, etc., and you see what's happened. So the original trajectory was this one, and then it becomes flatter and flatter at some point here. Okay, so this reminds very much this Kohne's cutoff proposal, which was this one. The main difference here is that the cutoff, so this flattening of the trajectory here as U is increased. So let's say essentially would like to send U to infinity. The cutoff is level dependent. So it puts a natural cutoff, but the cutoff is level dependent. Okay, so you will have another trajectory, higher energy, which will be completely outside with this trajectory. Okay, so it's similar to the Kohn proposal, but it's implemented by a new parameter in the Hamiltonian. And then everything went up well, at least for our minimal goal. So essentially, as you increase U, you see that the first unwanted term, they come at level log of t over t to the power U minus 1. So formally, if you send U to infinity, you drop all this term and it remains only the standard series. Okay. The drawback, it's a little drawback, it's probably not so important, that the linear term has been modified. So in the limit U going to infinity, you have a little modification of this term. So we don't get exactly the smooth part, but we get the smooth part apart from this linear term. Okay.
So what is the value of epsilon here? Is it 1 over 8 pi?
Yeah, it's the same, yes. It's the same as before. It's 1 over, yes. Okay, so this is the result. It's coming, of course, from this symptotic analysis. Although we don't know exactly, we don't know whether it is really an exact result or not. I mean, we hope. Usually when you are able to resum things, it's so the model is also, I don't know, not very complicated. So I can arrive to my conclusion.
So when you use very, for example, when you use 8, for example.
Yeah,
then
if you get the
opposite one.
we check up to U equal 22.
Oh.
Okay. Okay, so I think it's quite convincing. I mean, maybe there was some mistake in mathematics, but I don't think so. There are many checks we did. So I can arrive to my conclusion. So the first obvious question is whether this is the exact result or not. Okay, in the limit when u goes to infinity. So essentially, the main question is whether this this function is really equivalent. It's giving you an exact quantization condition. Okay, exact quantization condition are usually like a exact Bethe-Ansatz equation. So the next step would be to find, for example, the TQ relation. It shouldn't be too difficult to find the TQ relation for such a spectral problem. And then, of course, I'm also interested in this, so the IM setup, so this correspondence between ordinary differential equation and the integrable model. I think I've done with the.
What's the role of epsilon in this analysis? The epsilon independent? You can choose any epsilon?
Yeah, epsilon is epsilon, you mean? Yes. So epsilon is at the beginning is dependent, but we fix it to get some nice coefficient that is in agreement with the smooth counting.
So U goes to infinite limit is independent from any epsilon.
Yes.
Although, for example, you can take epsilon goes to general limit first and take U goes to infinite.
Yeah, if you send it to zero, you get again the
ordinary
oscillator. Yeah, well, it's not really the oscillator,
yeah, but
because you have
U and it's stuff.
For U equal 2.
But still, the same that spectrum is same number of states and so on.
The number of the states, yeah, I don't know. We didn't study much. So when it's
also this is for some specific value.
So this is for this epsilon equal 1 over
exactly.
Okay, so this is, essentially we notice that this value, for this value of epsilon, we could get some coefficient, and we carry on fixing that value of epsilon. But again, you have a much wider family of the quantum system.
Questions?
Yeah.
So, the direct quantization might be difficult, but nevertheless, let's say if we can diagonalize, I mean, if you quantize the system, and what was the NT plus, like in the last moment you talk about is NT, which is calculated from the WKB, but if you really directly quantize,
Yeah, I don't know.
This NT is just energy, or what was it?
Yeah, this was the N, which I elected. This was the N when it was this. Yeah, small n equal 4 times n capital N minus 1. Okay, and then essentially from exact Bethe-Ansatz equation, you can read immediately what is the counting function. This you can do even for integrable models. Just you consider that n as a function, and there will be an integer at the, when you cross one eigenvalue. It's a bit like, I don't know, if you to the Vega counting function, it's an object which is counting. Okay, so I think maybe I missed to show that step, but I think it's a standard fact that
But from the directed quantization, how can we find this NP function? Is there a way, or?
Yeah, I don't know how to directly quantize the system, because if you expand it either in epsilon or in U, then you have a differential operator which is infinite order.
Yes.
Okay, so I don't know how to quantize it apart from the Weil quantization. So that's I don't know. Yeah.
And just in principle, if someone like a genius, so that give the quantization, then from that quantization, either how can we resolve this NT either?
So so, well, in the same way. So when you quantize, you have some object which is equal to an integer or integer power plus 1/2, and you elect the left-hand side minus 1/2 to be your counting function. So it's so the counting function is something which is an integer, give you an integer. So if you take the log of the counting, yeah. So the spectral determinant, you get any. It's maybe we can discuss it.
Yeah.
But this is not difficult. Even if you do the harmonic oscillator, you always something which is n plus 1/2 equal to some object. Okay, you subtract 1/2 and you elect the object to be your counting function.
Yes, one other question. So I guess you pointed out that the counting function, so this model seems to reproduce the counting function for the zetas, which, as you said, doesn't predict where the zeros are. So it's just some coarse-grained information.
Yes.
Do you think there could be some other observable in this model that has other information about zeta? Like, for instance, it's known that the correlation function along the critical line, if you look at x and x plus y, there's like some sine kernel, like sine y over y for the correlation or something. So would you expect that some other data about the Riemann zeros would also be encoded in this model, or maybe just the counting?
Well, I don't know. I don't know. I think, I mean, standard treatment of this very heating Hamiltonian, historical treatment or proposal for this self-dual Hamiltonian related to the zeta function, they always concentrate on the spectrum.
Would you comment a little more about the item 3, that is the Baxter TQ and ODE?
Okay, so essentially, theta contains the ratio of two gamma functions. Okay, this is so the quantization is the ratio of this gamma function. Then there is some log of it, then is equal to 1. Okay, that's the quantization condition. And then usually and this is a Bethe-Ansatz condition, and usually when you have a Bethe-Ansatz condition, you can guess what will be the TQ relation, right? Okay, so you have to write in the term of Q plus Q minus equal to something, and something is proportional to Q. And if you have SU2 symmetry, maybe that's not too difficult to do.
But in the ODE-IM part, that since you have a kind of harmonic oscillator,
In that case, an harmonic oscillator. Yeah.
And you are trying to construct some Hamiltonian.
Yeah.
The Schrödinger equation.
Yeah, I'm trying to generalize the ODE-IM with this more strange model.
Higher derivative to the one over even non-local sense.
Yes. So maybe for next step is two oscillator.
Sorry?
Two oscillator.
Two oscillator.
Yeah.
Yeah, I think I mean, I was a bit surprised about this numerical result for negative epsilon. So with this continuous spectrum. So maybe with two oscillator, we can, move toward a 2-dimension and understand more about it in 2 dimensions.
4-dimensional phase space.
Yes.
This deformed Hamiltonian, including you, could you motivate it a bit more, by how is that cooked up, or is that a familiar Hamiltonian?
So whether I can perturb it with another parameter. Yeah.
Deformed Hamiltonian,
Yes.
How was this cooked up? What's the motivation like?
I was.
The Hamiltonian which depended on you.
Yes.
I'm just asking, how is that motivated? Is that a familiar object?
Yeah, it's a family of objects, but we don't know. I mean, for us, as I say, the minimal goal was to eliminate the term we couldn't understand in the expansion. but yeah, it's a,
In what context does that come up like this?
well, yeah, I don't know, the patient, that was- So, yeah,
But he is.
I think similar Hamiltonian comes from TT bar perturbation in R dimensions.
But here there are two parameters, right?
Yes.
There's an additional U parameter. Does that also come from a flow? Or?
Yeah, U parameter is usually in TT bar either there is also an alpha. So if you take the derivative of the Lagrangian, you take the determinant of P to some power, then you have a new degree of freedom, and that gives some Lagrangian, which is more complicated, and instead of having square root, it has cubic roots or.
That's